brings us to the next part of this, which is the final inquiry question, chemical synthesis and design. So chemical synthesis and design, it's a very small little inquiry question. What are the implications for society of chemical synthesis and design? But it's a very strange inquiry question, and I will go through why. It's because it's basically evaluating, and it's very difficult to think of questions for this, example, practice questions for this. I got one in my HSC that was kind of a curveball, but I'll go through that later. Basically, the factors that you need to consider are availability of reagents, reaction conditions, yield and purity, industrial uses, environmental, social, and economic issues. And things to keep in the back of your mind when you're going through chemical synthesis and design is Le Chatelier's principle, which is important because when we talk about yield and reaction conditions, this is key to figuring out what gives you the highest yield and what best reaction conditions are they. And then necessary reaction conditions for organic reactions. For example, if you need catalysts, if you need it to be in the presence of, let's say, acidified permanganate, reflux conditions, all of that kind of stuff. Like if there needs to be dilute sulfuric acid, things like that, you need to know. And then monitoring and managing chemical reactions. So this goes back to our monitoring the waterways and all that kind of thing. If it produces toxic waste, so let's say that the industrial process that you're doing ends up in the formation of carbon monoxide that you'll just release into the atmosphere. Is that the best synthesis chemical design? Probably not. So you need to find ways to use up those toxic chemicals or prevent them from being just released out into who knows where. So we'll go through each of these factors individually. The overarching, I guess, process that you should think about when doing this part of the syllabus is the Haber process or the Haber-Bosch process. So that's the equation for it. Know that equation off by heart. Know that it's exothermic, and know that it requires an ion catalyst, and that the best reaction conditions for it are low temperature, high pressure. And basically, all you need to know is that ammonia has lots of uses, particularly with fertilizer, and it's been used as a fertilizer for a very long time, especially in producing food during the First World War. And yeah, so if you know that it's exothermic, ion catalyst, low temperature, high pressure, know the equation, know that it can be used as a fertilizer, and that's it. That's all you need to know about the Haber process, and you'll be able to evaluate it. So first factor that it said to go through was the availability of reagents, and this is important, and it also ties into environmental factors. I'll get to that in a second, but it's important to figure out where your reaction will be located because of how available the reagents that you need for the reaction are. So you don't want to be doing your reaction in a factory that is in a different country to wherever the reagents are, because then you'll have to spend money on importing those reagents, and spending that money is not good economically for your chemical synthesis design. Then on top of that, transporting it will be horrible for the environment. Think truckloads of whatever you're transporting, all that emissions. Like, there's so many things that could be reduced, your environmental impact and your economic costs. All of that can be reduced by choosing a reaction and a reagent that are close together. So keep that in mind. An example is polyethylene from ethylene. It can be sourced from biomass and fossil fuel sources, and obviously this will depend on location and availability, so choosing a place where you'll have that availability is important. And in ammonia, nitric acid used to be used to get nitrogen, so they went through another chemical reaction to produce nitrogen from nitric acid, And in doing this, they could make ammonia through the Haber process. But the important thing was that that first reaction to get nitrogen was something that you would evaluate when you talk about the availability of reagents, because it wasn't the reagent, nitrogen was not readily available. You'd have to do other processes, which would cost money, cost time, all that stuff. So something to keep in mind. Next thing is reaction conditions and yield. So it's important to consider what reaction conditions will cause the best yield, and also the best reaction rate, because you want it to go fast. So you'll often think of this with collision theory and Le Chatelier's principles. So ammonia production through the Haber process is exothermic, and when it's exothermic, it means that it works best in terms of yield at lower temperatures. So that lower temperature is not good in terms of reaction rate. That means the rate of reaction will be quite slow. So you have to compromise between wanting that great yield but also wanting the fast reaction rate. Then, basically, another thing to consider is that high pressure, which is favored for the Haber process in Le Chatelier's principles, that is super important to consider, because high pressure is expensive. High pressure is so expensive. So you don't want to be spending that money. You want to make a compromise, and that's why the overall reaction conditions are 400 degrees Celsius and 100 newtons. I mean, not 100 newtons. 100 MPa. Why do I not know what that means? 100 MPa, yeah. And another thing to consider is if it requires a catalyst. The Haber process requires an iron catalyst, so that would increase the reaction rate, drive it forward. Another thing is that during the Haber process, what happens is the gas ammonia that is produced is changed into a liquid and collected as a liquid basically immediately. And then once it does this, it's removed. And once it's removed from the system, this will cause Le Chatelier's principle to work. And when it does this, once it works, it'll basically just like shift right to produce more yield. So Le Chatelier's principle is really important. It just helps you figure out what reaction conditions are best to produce the best yield. Okay, so the next thing is yield and purity. So the quality of reagents, and also whether or not another product is made in the process. If another product is made, it's important that you find a way to remove that so that it still has high purity. For example, when synthesizing something by a hydration reaction, there are other products. So you want to make sure that those products do not affect the yield or purity, that you get rid of those products in some way, shape, or form. Another thing is with the Haber process specifically, gas molecules are filtered to remove contaminants which may damage the catalyst, and this may decrease the purity. So all things to consider while going through and evaluating chemical synthesis. Another thing is industrial uses. Basically, if there's no use for whatever you're synthesizing, it's not worth making it. So another thing is if it requires high purity, then you'll need to consider if the industrial use requires higher purity, then you will need to consider different reaction conditions than if it requires lower purity. So cheaper soap would obviously be less pure than more expensive soap. So you would use a different process in chemical synthesis for those things. So as spoken about earlier, ammonia is used for fertilizers. and it's used in lots of fertilizers. It's very good for fertilizing, and it was really needed in the time of World War One because they needed lots of like food, I guess. So in the context of the Haber process in World War One, ammonia was used as a fertilizer a lot to make sure they had enough food. And the Haber process is thereby driven to be as economical and widespread as possible, because during the war, obviously, they're spending so much money on the war and on the fighting, they don't have money to spare on making sure that they could have a very, very expensive synthesis. They needed a cheap synthesis design, if that makes sense. They needed it to be cheap. So that's why you need to consider the industrial uses, because yeah, like it's pretty self-explanatory. They wanted it to be economically viable in that kind of time period, and therefore it occurs at a lower pressure even though it might not provide the best yield. And that's because also with the industrial uses, it's being used as fertilizer. Like, the purity doesn't matter too much because it's fertilizer, and at the time it didn't matter too much because they really just wanted fertilizer to be able to just grow food for the soldiers. Like, they weren't really picky about that kind of stuff. So that's just something that you need to consider. Next is environmental, social, and economic factors. So yeah, this kind of ties in with everything else, like I said, about the cost of transporting it if your reagents aren't available in a close by area. Also, like the emissions of transportation and social concerns, animal welfare, all those kinds of things. It's pretty self-explanatory. It's just you need to make sure that you're not harming the environment. Let's go back to my example of carbon monoxide. If your synthesis process requires you to release a ton of carbon monoxide into the environment, you're not only killing the atmosphere, you can also have very substantial impacts on animal life and human life. And so, is that really ethical? That's something that you have to ask yourself when doing chemical synthesis and design. You don't want to be producing toxic waste. You want to be able to remove that and be able to use it for something else. So what made the Haber process successful was that it used less power, less complex equipment, cheaper reagents. It was so much better than other nitrogen fixing processes, and in the context of the war, it was so useful as well. And on top of that, it's like the economic part is really important in the war. As a modern history student, this is very like what I used to talk about. But anyway, main thing is consider the environmental, social, and economic factors. There's really not much I can say about it, because when you get a question about this in the HSC, it's going to be something like the question I got in the HSC, which we'll go through in a second. It's never going to be something super specific. It will be evaluating, and you just need to know things like Le Chatelier's principles, what environmental, social, economic factors means, what availability of reagents means. You just need to know what it means, and then we'll get to the evaluation stuff in a second. So, okay, we'll get to the evaluation stuff in a second. It's coming up in the PowerPoint. First, we'll do these revision questions for 8.2. So this is a HNMR diagram. It has 4 clusters. Those 4 clusters means 4 unique hydrogen environments. If you look at the drawings for the 4 molecules on the side, you'll see that there are, most of them have more than 4 hydrogen environments. So if we look at A, this is a hydrogen environment, this is a hydrogen environment, this one is one, this one is one, and this one is one. So that's 5 unique hydrogen environments. That's more than 4. If we look here, this is a unique one, 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 and this is a unique one. That is 1, 2, 3, 4, 5. That is 5. That is more than 4. If we look at C, these two are the same. This is the same. So that's 1, that's 2, that's 3, and that's 4. So therefore we have 4 unique hydrogen environments. And that means that C is what we're looking at here for the HNMR. If we look at this, which is a CNMR diagram, you have your, again, 2 unique carbon environments. And which of these has 2 unique carbon environments? So we start at the top. This has 3 unique carbon environments. This one here, and this one here. This one has 2 unique carbon environments. Let's keep that in mind, because maybe there's another one with 2 unique carbon environments. C has 1 unique carbon environment, because this is symmetrical. This is the same. And same with D. So B is our answer here. Okay? Now, this is revision for naming the unknown compound. This is a past HSC question. Basically, if we look at this, we ignore the fingerprint region. First, we should look at mass spec. We'll see that the molar mass is 86, and we should keep that in mind. Then we'll figure out how many carbons there are based on that. Then we've got the infrared spectrum. If we look, you'll see that there is a C double O bond and a CH bond. This could mean multiple things. An aldehyde or a ketone. Could be either, but we'll see. Then if we look at the proton and carbon NMR spectrum, see that there are 3 unique hydrogen environments and there are 4 unique carbon environments. So this already tells us something. This tells us that there's some sort of symmetry happening. There is a hydrogen environment where there's like 2 that share that same unique kind of organization, because there are 4 carbon environments and 3 hydrogen environments. Anyway, basically how this works is if you look at the mass spec, you'll see that it's 86. That mass of 86, if we say that it's a ketone or an aldehyde, that means that there are 5 carbons. Okay? There are 5 carbons, so those 5 carbons, we move on to figure out, well, is it just straight up pentanone? No, it is not, because of the splitting pattern that it shows and the carbon NMR. So that means that there's a methyl branch somewhere, because there are 4 carbon environments and 5 carbons in the molecule, so there has to be a methyl branch somewhere. And basically, you look at the proton NMR, you have one most chemically shifted, which has 6 neighbors. You have one that's the next chemically shifted, it has no neighbors. And then there is a doublet at the end, 1 neighbor. So all of this really comes down to, oh, I didn't have the answer up, but I will tell you the answer. It's 3-methyl-butane-2-one. So if you draw that out, you'll see that it all works out to be like corresponding to these what are they called? Diagram. You'll see that it all works out to correspond with these diagrams. But again, how you approach these is just draw it up and then it'll make sense. Now, back to the chemical synthesis thing. This was from the 2022 HSC, and I did panic when I saw it because it was 8 marks for something that I did not spend that much time on. So basically, analyze how a student could design a chemical synthesis process to be undertaken in the school lab and then relate it to an organic compound with a chemical equation and refer to these things. So I chose esterification because I knew those reaction conditions really well. So I could easily talk about the reflux conditions, the sulfuric acid that was needed, also that heat was needed. You do it on the in heat. It needs to be heated up because it needs to be vaporized, I guess. Anyway, so reaction conditions for esterification were quite clear, and you should know that from organic chemistry. Then selection of reagents, it's pretty easy. You have a carboxylic acid and an alcohol. Those are very ready in a school lab kind of setting. It's not something that's too hard to obtain for schools. Then potential hazards, you have the fact that you're dealing with hot stuff. So I could talk about that. You talk about how if you don't cool down the alcohol that's getting vaporized, inhaling alcohol might be bad. You should open up the windows, do it in a fume hood, those kinds of things. Also, if the gas gets out, it could be volatile. I mean, it is volatile. Gas gets out, it could be flammable. You don't want it to be near an open flame. All that kind of stuff. Basic school lab rules. You can just talk about there. So that's just what I did. And then yield and purity of the products. You can evaluate this and analyze this by saying things like, how do I know that the end product is all ester and not some runaway alcohol that was just volatile and ended up being put with the end product? So it's like there was quite a bit to talk about for that. But when you get a tricky question like this, a sort of curveball, if you will, you just need to go with what you know. So don't try to find it. Asks for an organic compound for a reason. It's because there's not many options when you have to talk about the synthesis of an organic compound. There's not many options in a school setting. They're kind of giving you a hint that you should probably be doing esterification. And esterification, if you know the reaction conditions, you're good. Like the fact that the ester is removed and it causes like Le Chatelier's principles to favor the formation of the ester as more of it is being made and being turned back into liquid form. All of that stuff, it's all good things to talk about. Getting to 8 marks, I don't actually know if I got, like I could have gotten a 4 out of 8 on this question. I don't know. I didn't get my paper back. But from what I read in the marking criteria, I did answer the question. So hopefully I did well on that question. But yeah, 8 marks worth. Make sure that you put in the chemical equation because it asks for it. That's like 100% a mark. And don't forget to add in your states because that's very important as well. But yeah, this is the type of question you get for chemical synthesis and design, and it's a weird one. It's really weird. So just keep in mind that chemical synthesis and design is a very weird question, and like it's a very weird part of the syllabus, and you'll get weird questions on it. So you just need to be prepared to analyze the information that they give you on the day. Like you can't really prepare for it other than knowing your Haber process and knowing its reaction conditions, because if they ask you to provide an example, Haber process is probably the best way to go.